All right, let's get started. Today we'll talk about ICMP and some ways that we will encounter it in the real world, in the wild. And at the same time, there was a request to talk about the next homework. I decided we'll do a TCP ping. So it's a bit like ping, but we don't send ping messages like ICMP messages, which we'll find out in a moment how that works. We'll send TCP packets instead, but we'll have to deal probably with some ICMP packets coming back because there will be all sorts of error messages. So an advantage of TCP ping over, that's the right one. An advantage over TCP ping over ICMP is that usually end hosts don't really have much of a choice when it comes to TCP. Like if you're a web server, you're going to have to respond to port 80. You can't really do much about that. Whereas they can decide to respond or not respond to ICMP. So we can probably get a little better response rate with TCP ping. At the same time, it gives us some good practice with dealing with packet headers and sending raw packets over a raw socket. So this is a raw socket is where you basically get to send a raw IP packet. In fact, you can also tell it I want to be able to send raw Ethernet packets. That just means you need to put an Ethernet header on it as well. But I think we'll stick with IP packets for now. So with a raw socket, anyway, you get to both send and listen to any IP packets that come into this machine. So that should make for an interesting exercise. I haven't written it up yet. If you want to get started, the first thing to try is open up a raw socket. You'll find Linux documentation for it. Send a SYN packet to a web server, some IP of a web server and port 80, and you should get a SYN packet back, and that's a ping for you, right? Then we have a round trip time and we're good to go. So that'll cover much of it, and the rest is we need to deal elegantly with various error cases where say the network isn't reachable, or the host isn't reachable, or the host isn't listening to that port, or sort of thing. Okay, so let's see, what do we do? Why don't we take make a little experiment with some ICMP here. I think we can do this. Okay, so I'm telling it I want to listen for any incoming ICMP packets. ICMP is the Internet Control Message Protocol. It's not really meant for applications, though naturally you would have some administrative applications like ping that want to talk ICMP. It's more meant for hosts to hosts or routers to hosts, maybe hosts to routers. I can't think of a case of that. Where you basically, they want to do some control messaging saying, oh, you probably shouldn't send these packets to me, send it that way. Or, by the way, I'm not listening, right? That sort of thing. It's not for applications to worry about. So the archetypical ICMP message is ping. And it looks something like this. In fact, let's see if we can, I wonder if I have Wireshark on this machine. Yes, I do. Wireshark is, no, I don't. That's weird. Okay. Actually, maybe I could do it like this. Right. So anyway, ICMP, it looks something like this. So the IP packet would have in the protocol field, there's an 8-bit field that says what's coming next, UDP, TCP, in this case ICMP. We don't see that here. And then comes the ICMP header, where you would otherwise see a UDP header. So there's no TCP or UDP for ICMP. It's a separate alternative. There's a couple things that could be, a few things that could be happening, but basically the main information we're interested in is the type and the subtype, the code here. So it says, oh, error code this, subtype this, right? And then there could be some extra information passed along, that depending on the error. So what are some typical messages? Ping, right? Actually, where's the echo request? Okay, so ping is the 8, right? Type 8, no subtype. And you get an echo reply, 0. Right. So let's see if we have that here. So here it's, they decoded it nicely from the number into a string, but okay, we will live with that. Let's see how this install went. Oh. Okay, so Wireshark is just is basically TCP dump, but it is a little more interactive. You can kind of drill into the protocol headers. I thought it might be cute to demo. We'll see how that goes. All right, so that's pretty straightforward. So the expectation when an operating system receives a ping packet, one of these ICMP echo requests, is to send back immediately a response. Sometimes they don't, and then we have to live with that. There's no server running on the machine that responds to the ping. This is the operating system has this built in. You don't need to run a ping server in order to get a response back. I think in some OSs you can disable it, and maybe it's that some firewalls disable responding to ping for whatever nonsense security reasons. Here we got another ICMP message here. It says, oh, UDP port blah unreachable. I don't know that we were the ones that requested it. I don't know my, oh, here. It's the DNS that says this port is unreachable. So why did someone try to send a packet to that port on a DNS server? Who knows? But this is what ICMP is for, to say, well, that probably wasn't right. Okay, let's try that actually. Really? One more. Wow, this is... Okay, let's try... Yeah.
So who sent that weird 61,248?
It's possible that it's my machine. Let's see, that's the IP address that's sent. Let's see that. Oh no, it's the other way around. This machine responded to the DNS machine saying it's unreachable.
So I thought the TCP dump was doing it on your machine.
Yeah. So depending a little bit on the network setup, on a wireless network, you can sometimes receive messages from anyone on the wireless network. I suspect that's not the case here, but I'm actually not familiar with what the wireless setup is. It's more likely that it's my machine. So why don't we take a look at that? Too many network interfaces. It should be here somewhere. Come on. 10.4. 238.223. Yeah, so that was my machine. So the DNS server, probably what happened was the DNS server was responding to some request, and my machine already had stopped listening to the port. Who knows why that happened. Okay, what were we doing? Right, so I wanted to SSH to Google. See if they like that. They don't even want to tell us anything about it. It's a shame. Let's try another port. Yeah, they're not being very responsive. Yeah.
In the article, under the structure section, it mentioned the header. It discussed IPv4, but it doesn't mention IPv6. Is it not compatible?
There is an ICMP version for IPv6 as well, ICMP 6. It's, I guess there will be a few little differences, like in the message part. I would imagine the types are the same, but in the rest of the message, you need to have room for a bigger address sometimes. Right, okay, so this wasn't too exciting. Let me see if we can come up with one exciting case. At least get a response. Okay, that was good. Oh, what? And then we didn't get a response from that either. Okay, I guess here we got a reset instead, a TCP reset probably. Yeah, not sure. See if we can try. Let's do something completely different instead. So traceroute is another application that relies on ICMP. Here, it doesn't really matter what message you're sending. In fact, I don't know what message we're sending out, but I would imagine it's just a UDP packet or a TCP packet going to its destination. But along the way, let's bring up the IP header. So that the IPv4 header looks like this, right? There's the protocol that we're talking about, selecting what's next. But there's also a time to live, and it starts out at something reasonable, maybe 32, something like that. And then it counts down. Every time you pass a router, it counts down by 1. And then when it reaches 0, the router ideally sends you a time to live exceeded ICMP message back. Like, where is it? Time exceeded. Here it is. So type 11 and then 0. TTL expired in transit. So the trick is when you send out these packets, we send them in raw mode here. So the OS won't just send anything, send their default number for the TTL. We get to set the TTL, send a packet off to the destination, but with increasing TTLs. And then routers along the way send back a response. So let's try that. I'll just set it to only send 1. Usually traceroute sends 3 packets for each destination or for each number of hops, and it waits for quite a while for each one. So to speed things up, we'll go like that. All right, so we did this early on in class. So here we have all of the hops along the way to this university in Sweden. And if we look at traceroute, we'll see there's a ICMP time exceeded for the various hops, right? And we don't see if there's, they look a little bit different. It's probably just that these host names are longer, so it kind of makes it align differently. Yeah, that's what it is. Okay, so anyway, we're getting these, but one from each host along the way to the destination. Let's see what else there is in here. Most of these, perhaps, you wouldn't run into. Echo reply all the time. Destination unreachable, these are common, right? You would often get these errors. You try to connect somewhere, it says destination port unreachable. That is not something that your application usually sees. But what you see is you issue a connect call, right? And you get a -1 back, and then you check the error number, and in the error number it says something like this. So it's not that you're directly talking to the ICMP part of the OS, but the socket API will report something based on that to you. So most of these you probably wouldn't run into, but these are very common. Okay. We didn't talk about fragmentation. It's not something that is very commonly encountered. If you send a packet that's too big, then the network along the way will chop up the IP packet into multiple pieces, and you get this increased fragment ID here, the fragment offset. So it says, oh yeah, I chopped this up, so here's byte 100 and on your IP packet. If you send something that's more than 1500 bytes, then you will probably either run into packets dropped with an ICMP message back, if you're lucky, saying like this was too long or fragmentation required. Or it might just chop it up for you, and then if you get lucky, it gets reassembled correctly on the other end. Of course, if you lose a packet, part of that packet, if you lose one of the fragments, then probably you end up losing the whole thing. And because of these reasons, people try to avoid fragmentation, try to send smaller packets instead, or at least check. In fact, we can check whether a path to a destination can support a bigger packet by just sending increasingly larger packets until we start seeing fragmentation and then backing off. Right? So that's it's called I can't remember the name for the technique, but basically you probe for the size, the maximum allowable size on this particular path. The internet in general doesn't have a specific size that it always supports, but 1500 is common. Okay, what were we saying here? Right. Let's go through the rest of the ICMP things. That there was a couple of things that are kind of interesting. The redirect I actually ran into just the other day. I was trying to set up this experiment that we were doing. We're routing from one machine to another machine and then onto the internet. And that works fine as long as you tell the machine to do IP forwarding. I think I demonstrated that in the end, I'm not sure. But what really happens, interestingly, I'll try to draw something. So here we had our gateway, right? And I was routing from my machine nodes to my machine frames. And all of these are on the same subnet. Back? Hello. Right. So this is the /24 subnet. All these machines are on the same subnet, so nodes really should be sending it messages from here to there. But then we changed the routing, and we told it, oh, you should actually send from here, and then frames will forward it this way. This is not something that Linux really appreciates, because it looks a little weird. So frames gets this message from nodes, and it says, well, why don't you just send it straight to the gateway? This is not my problem. And in fact, there's an ICMP message specifically for this. This is not my problem. See here, redirect, let's see, datagram for the host or network. I'm not sure which one we got. But basically it says, oh, you don't need to send it to me. You can send it straight there and it'll work still. And that's what actually happened. I didn't show this in class, but I was extremely confused for a long time talking to lots of people because we weren't familiar with this particular redirect thing. And eventually we figured out what's going on. So worth keeping in mind. See what else we have that's somewhat interesting. Router advertisements, those are important in IPv6. Right? On a subnet, a router will advertise its existence. Say this is the subnet, this is the local subnet, and I have a route to the internet or something like that. The router solicitation, same thing. If you want to hear from a router, I think it'll periodically send something out on the network, or you can ask it, and then you'll get a response immediately. See if there's anything else important here. You see, many of these are deprecated. I think the reason for this is that the more complexity you have in ICMP, the more you need to put stuff in your routers. Like routers are supposed to comply with ICMP, and And every time you introduce more code in a router, it gets a little more complicated. It's more likely to have a security vulnerability or break in some other way. It's better to keep it simple. And some of these are maybe a little dubious from a security point of view as well. It's not clear that you should be able to ask about all the routes in the network and so on. Yeah?
Can you mention again, or I'm not sure if it was mentioned, so we have these control messages. Are they processed at the receiver end? Like how are these messages used?
Yeah, they're mostly sent as a sort of notification. It's not to make a change anywhere. It's mostly to say, oh, and by the way, I dropped your packet. In the case of the redirect, it's sort of a suggestion. Where's the redirect? Here. It's a suggestion from a router along the way that you send it that way instead. You don't have to do it. It forwarded the packet for you, but yeah, you might want to follow that suggestion. Okay, I think that's about it. So ICMP is handy for a thing or two. While we're on this topic, I thought we'd run this for a little bit and just see something more about the internet topology. We've talked about autonomous systems. We talked a little bit about ICMP here and what the route looks like. I thought, why don't we try to see which autonomous systems are there along the way, see what that can look like. So if I run this with -n, I get a bunch of just IP addresses. So these are the routers along the way. The star means we didn't get a response. What do you think is going on here? Like, why didn't we get a response for all these hops? Yeah.
TTL like right now?
No, that's when you get a response, right? So here we had a TTL of 1. We sent a packet with TTL 1, and we got a response saying, sorry, dropped your packet, right? And then eventually we get to 24, and now we're not getting any responses anymore. Yeah.
It's a private network or some network that is not responding to ICMP packets for security reasons.
Right, yeah, it's not responding, that's true. But it seems like kind of goes on forever.
It's retrying. It traces automatically.
No, it's not retrying. There's no, we told it specifically, just only send one. And in fact, the TTL is increasing here. We're sending, look, so many hops, no responses, yeah.
So they got our packet then?
Yeah. We've reached the destination. The destination host doesn't want to respond. So it doesn't matter how high of a TTL we specify, it still won't respond. Maybe if we do this with TCP instead. In fact, let's see what, let me do a very generous TCP dump here. This could get bad. Oy, oy, oy. Actually, I don't know how to deal with this. I wanted to try to run traceroute here. Oh, maybe it'll work. Let's get rid of crash plan at least. This is a backup software. Stop it. Okay, let's run this a few times. Maybe we'll get. I want to know what packet it is we're sending out. Okay, so we sent an ICMP. We got an ICMP back. Oh, here's the packet we're sending. It's a UDP packet of length 24. It says, oh, here's the port. Okay, so TCP, this TCP dump is sending UDP packets to some random port. Maybe we can tell it to send the TCP packet instead. Oh, pproto, there it is. Oh, no, that's not. Here. Okay, so let's try that. Let's try TCP, see if it does anything different. It'd be nice if it just finished. Maybe it should be before. Oh. Oh, that was no good. Oh. But if we're sending ICMPs, I wonder which one that is. Let's see. Maybe that's an echo request we're sending. Maybe we're sending pings. So take a look at that too. So that's an ICMP now. That's good. Yeah. So now TCP dump is sending pings, but it's exceeding. It's expiring along the way. Okay, let's use that because that I like it that it finishes. That's great. $2. Right, those are our hosts, and then I'm going to grep for origin, because I know sometimes it says origin AS, and sometimes it's capitalized O, and sometimes not. So, but origin should be pretty good. Okay, cool. So here we got some AS numbers. So these are the autonomous systems that own the IP addresses. I really should be printing out the IP address too. Let's do that. On the same line. The -n just says don't put a new line. So it runs through all the IP addresses, and then we see which autonomous system does it belong to. So you see there's lots of IP addresses that all belong to the same autonomous system, goes through a bunch of routers of the same network, right? And then we change network, go to the next one. In fact, I had a nice list of, here they are, autonomous systems here. So we could look it up. So we're spending a lot of time here in 11537. That's the Internet 2, right? That's the American University Network, right? And then we're going to 2603. Here. No, that says it says 32,000. Let's go AS. There we go. Nordinet, the Nordic University Network, and then AS 1653. Oh, I'm sorry, I said too small. Huh. It doesn't want to. Oh, okay. Ah, go back. AS 1653. Okay, there. That's the Swedish University. Really? Oh, Swedish University Network? Okay, fine. And then maybe we'll leave it at that. There was one more. Let's just see which one that is. Previous. Nice. Good job, alma mater. Okay, I guess they somehow advertised their name a little wrong. Okay, so here we can read about the, which IP addresses belong to it and so on. But I don't know why the zoom level isn't working the way I want it to anymore. Okay, so general idea is we passed through maybe, that's probably UIC here. So 1, 2, 3, 4 kind of unique organizations along our way to this university in Sweden. Yeah.
IPs have 2 or 3 autonomous systems.
Yeah, not sure what that means. I think that these autonomous systems are both the same autonomous system, but that they have two AS numbers for some reason. Why don't we look at that too? It's not being very reliable. Okay, so there's Internet 2, a long one, Transit Rail CPS. Okay, and then this. $11,537 there, and that's also Internet 2. So I guess it's kind of split into a few pieces. I don't know why they do that, unfortunately. Right. Okay. So that gives you sort of this flavor of this big central networks. In this case, there wasn't actually a big central network doing any work here. The Internet 2 is big, of course. It's not nearly as big as, say, Sprint. And it has a direct link to the Nordic University network across the Atlantic. I'm pretty sure they don't have their own cable, right? So they rent out fixed capacity. They say, okay, give me part of your optical fiber. I need a gigabit per second, and it'll be just a direct delivery point to point between, say, Denmark and Boston or something like that. UIC actually has something similar going from the EVL to Holland. I think we have a 100 megabit dedicated channel to over there. At least we used to. So you can buy all sorts of services. That's not an internet service, just pure connectivity, and then you can use that to route whatever you want. Okay. Going back to, let's see if we got this Wireshark to work. It's kind of nice, so give that a shot. Okay, here it is. Yeah, okay, capture this one, go for it. No package. Oh, is that how you shark it? Okay, so now it starts recording, and we'll run our trace route. Stop it. Pause the recording, and then we can take a closer look at. Let's look at this time to live exceeded. All right. So here's the structure. This is too small, isn't it? I don't know that I can zoom it. But maybe there's a font size here. Ah. Look at it, nice. I can zoom it, awesome. Okay, so what does it look like? This really tells us everything about this packet. So the entire packet looks like this. It's 642 bits. In fact, there's an Ethernet frame, and the Ethernet part of this packet is in the beginning. Okay, let me go back to here. It's in the beginning. That's the header saying what's the destination Ethernet address, what's the source Ethernet address, and what's the next protocol that comes. Usually it's IPv4. Okay, and then at the end, there are a few more bytes. I can't move my pointer. No. At the end there, we have another 8 bytes, and I think, I don't know about the 8. Maybe it's an 8-byte checksum. I thought it was shorter than that. But anyway, it's certainly part of that is the checksum for the packet, and maybe there's something else that I forget. Let's open this up and see what else is in it. Okay, so there's something called a trailer. Don't know what the trailer is for. And then we have our checksum that says, like, the packet should look like this. Like, make this CRC computation over the entire contents of the packet. You should end up with this number. If you don't, that means a bit somewhere in the packet was modified or kind of got screwed up along the way. Better off dropping this packet. Okay, backing up again. The IP header comes after, right? So byte 0 is part of the Ethernet header. And then a little bit later, at byte 20 or some, a little less than that, comes the beginning of the Internet Protocol header, and you recognize these kind of header fields in there, but perhaps this one is the important one. We know what the next protocol is that's coming. It's ICMP. And then finally in the ICMP request, ICMP packet, it says, oh, the type is 11, code is 0. That's exactly what we was kind of hoping for. And then there's nothing actually inside of the body of it. Oh, sorry, no. There is something inside the body. It sends back the beginning of the packet that we sent. It wouldn't send back a whole thing, but it kind of gets the header and maybe a little bit of the message saying like, oh, this was the packet that I dropped. Right. So here we actually sent ICMP packet as well, and I think that was the echo request, right? So let's see. Yeah, there's the ping request. That's the packet, part of the packet, or maybe in this case the whole packet that we sent off. Okay, so Wireshark is really neat for just kind of getting a feel for what's going on. It's not great for if you want to automate anything, but it's cool for like manual inspection of a thing or two. Highly recommend it to just kind of play with. If you feel a little uncertain about like, oh, what's going on with when you send a UDP packet, what are the various header types and whatnot, just open it in Wireshark and kind of confirm what you thought was going on. Okay, let's drop out of here. Was there a question?
I was confused for a moment because it said ETL 238.
Oh, okay. It's possible that it starts out at such a high TTL. That would be strange.
Response coming back.
Let's see. So that would be in the IP header. Yeah. So that's interesting. It's a very high TTL to start with. I think usually you wouldn't. Let's look at our ping request. Here we're sending it out with, oh, that's the wrong one. That's the one, right? 13. All right. So we sent it out with a 13. Oh, I'm sorry. This is TCP dump. Sorry, trace route. So of course we're sending it out with a really short time to live. Let's just check that out. Let's run a new one, and we'll telnet to there, and just see what it says. Okay, so this was our SSH packet. How long was our TTL on that? 64. Okay, that seems more reasonable. Like this number should be something like the maximum diameter of the internet. How many hops do you expect to see on the route to the destination? If you send it with too short a TTL, you'll never get there. If you send it with too long, it might be sitting in a loop for too long, which would be wasteful. Maybe a good trade-off is you pick a reasonable number like this, and then if it exceeds, maybe you could try a larger number after. I'm not sure, but certainly you wouldn't expect to see any more than 64 hops on the internet anyway. Okay. Yeah, so I think the responses came back with a really high number just to make sure that the TTL exceeded message actually makes it back to the sender. That might be it. Okay, let's close this. All right, so I think that's all I've got for ICMP, unless there are any further questions on it.
When you said it stays in a loop for a long time if your TTL is too long, what type of loop would exist?
Yeah, so sometimes there's a routing misconfiguration. Like you might have, if you think of the distance vector routing protocol, you might have a link that says, or a routing entry that says send it this way, and then it's on the other end, and the packet gets over here, and the routing entry says send it this way. Usually that's temporary. It's sort of something that happens until the next routing update, until the next update packet is sent out. So maybe for a second or so. But during that time, you wouldn't want your packet to go around a ton of times. It might even use up the link so that the routing update can't make it. So that's sort of why we have this TTL, so that these transient route errors kind of don't cause a disaster. Okay, so I wanted to spend a little bit of time on queuing in the network. We won't do any queuing theory, but at least let's think a little bit about fairness before we move on to the link layer, which will be next lecture. So let's see what we got here. I got some nice pictures. Yeah. So here's, generally speaking, what's going on in the network on every router. Routers or switches, they will, depending on the design, they might have a queue on the incoming links. You have lots of ports in a router or a switch. So you might have a queue of packets that are waiting on the incoming link, one queue per link, or you might have a queue on the outgoing side, but in the end maybe it doesn't matter that much. Often there will be some sort of joint, more complex thing, but the abstract view of it is basically we have a flow of arriving packets coming in, and then we have departures that are at some fixed rate. Like the link can only go so fast. Right? So arrivals are kind of bursty. The queue is there to help smooth things out a little bit, and then departures happen at a fixed maximum rate. So what happens when we send packets at too high a rate? Well, the queue fills up, and then we start dropping packets, usually from the back. You could imagine other queuing policies too, I suppose. So how can we enforce some sort of fairness between links, right? Or between sessions? There's a couple of things to it. One is like, what is fairness, right? How should we define what is a fair share of a link, and then how can we implement that sort of fairness? So one thing we could do is we could try to label incoming packets with a couple of different labels, and we say these are important packets, these are not important packets. You could say TCP packets are important, UDP packets are not, or you could try to look at a flow and see what it's been doing, right? Or maybe look at the port, you see, oh, that's an FTP, that's not as important as this Skype connection. Or you could say, oh, this one has been going for a really long time, it looks like it's a file transfer, and this is a short thing that just opened up, let's speed that up a little bit. You may have noticed that happening actually on your phone. Cellular providers often have a policy where a fresh TCP connection gets high priority. And then if it keeps going, it slows down. So you may have noticed that it goes quickly initially and then kind of slows down. It's a big image or something. The latter part of the image comes slower. Okay, so this might be good way to do it, and then sort of when you want to serve these packets, you kind of take two from here and one from there, or something like that. Let's see. All right, more generally, something called weighted fair queuing. Fair queuing, in this case, we might classify arrivals based on the source destination pair. So we say every unique TCP flow should have its own queue, right? So now we classify for all the unique TCP flows, we give them each their own queue, and they add up like this, and then maybe for simplicity, we use the same weight on all of them, so every TCP flow gets the same throughput through this router. This would be, oftentimes this would be very nice, but usually it's a little too expensive. Keeping a queue per flow can be quite the burden. In a core router, you can easily imagine millions of concurrent flows, and many of those flows don't have a single packet in the router at the moment. Right. Things go through pretty quickly, relatively small buffer, so there are no packets from this particular flow in the router, and we still have to remember how many we've sent, right, to keep it fair. Or if we just sent one from this other queue, from this other flow, now there's nothing in it, and then comes another packet from that flow, we need to know that, oh, we recently sent one, so we should take it easy. So you basically have to maintain queues then for all the flows that don't even have a packet in your buffer yet. And so we can't afford that. That gets pretty pricey. But you could do it at the, sort of closer to the edges where there aren't so many flows. And that's somewhat common. Or you could classify it based on other things. So you could say, oh, I want to do like 50% to UDP, 50% to TCP. That's an easy one. Keep 2 queues for that. This is something that is provided in the Linux kernel. So if you want to experiment with it, you can easily set up these traffic classes, and it'll start limiting throughput of your big file transfer when you're watching Netflix, let's say. So you can easily do that on your home network, let's say. If you have a Linux-based wireless network router, you can set this sort of thing up. But it's not really clear that it's fair to give equal weight to every TCP flow, right? At least in one sense, it should be per user, I would think, right? Every user should get equal share. Is that more fair? Like, because I can open more TCP flows, and now suddenly I get more throughput. That doesn't seem quite right. So should it be per user then? No? Why should it not be per user?
Because the user could just open a bunch of.
But then it's no. If it's per user, then the user opens more flows. It doesn't matter.
Well, maybe some users use less bandwidth than others.
Okay. Yeah. Yeah. There are some particular users that use a whole lot of bandwidth.
Because you might have like somebody watching like Netflix. You might have someone like doing something very simple. So it'd be like a big disjoint too.
Okay, yeah, so that's a good point. If I'm not using a whole lot, we shouldn't give me a large chunk of the network to just not use. So we really need what's called a work conserving scheduler, so that if the user that is due to have a packet delivered doesn't have a packet, we pick a packet from someone else. So that's very good. But let's say that every user who is now competing actually has a packet to send at all times. So then how should we split it? So, okay, I think it's a reasonably, the per flow is one good one. Per user is actually a horrible one. Everyone being equal, Google should get the same as I get, right? That doesn't seem right. Of course, a user, maybe organization is something different. And so you could say per end host, but then one of Google's front-end web servers should still get more than I get, right? Because when I'm connecting to it, it's like I'm getting something. It's not just Google getting something. It's the users, it's the pair that are getting something. So you could argue that maybe every host destination pair should get a fair share. That might be a better choice than every TCP flow. But then I could just talk to more machines. If I want to get more capacity, I talk to more end hosts, right? So I talk to Google's web server 1, 2, 3, 4, 5, 6, 7, 8, right? And now I'm getting much more than everyone else. It's really not so clear how things should be fair. I think maybe on one link, you can somehow get it pretty clear. But what is fair on the internet as a whole is really kind of up for grabs still. I think probably it should be based on how much you paid. Right? Because if you didn't pay anything, you should get crap service. If you pay a lot, that means you're contributing a lot probably to the internet infrastructure in the end. So probably you should get more. But tracking that seems like a real pain too. And it's not quite progressive, is it? Just as I'll leave you with this. Here's a way that we can do the actual implementation. So if we're saying, oh, a user is allowed 15 kilobit per second. But the user sends like these bursts of 1 megabit and then nothing for a while, and then 1 megabit and then nothing again. So how do we implement, like what is the right design to give them 15 kilobit per second? One nice design is called a token bucket policer. It's, they don't actually have tokens flying around. It's just counting. But basically we say you get R tokens per second coming into this bucket. It's a reserved. This is just an integer, right? Stored in your router. So this flow has an integer that keeps going up by a constant rate all the time. And then there's a queue where incoming packets get to sit and wait. If there is a token in the bucket, when an element enters the queue, it gets sent immediately and the token is removed. Right? But if there's nothing, then it kind of accumulates as a balance for this flow. It's one nice design, nice sort of implementation of rate policing. Okay, if fair queuing and such sounds really interesting, I'm happy to talk about that during office hours or offline. Next time we'll talk about the link layer and continue down from there. Thank you.